So thank you, Coach Kevin Johnson, for joining us today and walking us through the Open Rocket software. What's the importance or the need to use a rocket simulator?
So the biggest thing that you get by using a simulator is you get to design your rocket before you actually build it. And that way you can check to see the stability of the rocket, and you can get a good idea of the performance to expect from the rocket, so you can make any sort of changes to design before you actually buy all the parts and spend the money and actually fly the rocket. So that's the benefit of doing the simulation software. It fits right into the design life cycle, where you want to test something, make a change and test something. You can do that in the simulation and then have an idea if it will work or not before you actually commit to building it.
Very good.
And so one of the things that you can do with Open Rocket is you can either design something from scratch, without having a set list of parts, or you can take an existing rocket or an existing kit and enter the information about the rocket into the simulation and build the rocket as you go. One nice thing about Open Rocket is it does have a database of parts, of sort of standard parts. That makes it very easy to select things that are from a manufacturer. But you can also enter in all of the information yourself. The downside of entering in all the information yourself is you have to know some information about the mass of the object, how much it weighs, the density, and things like that. I find it much easier to use an existing part, and then maybe you need to change the length a little bit to meet what you need, but it allows you to make those sort of changes as well. So I see you've got your green eggs and ham rocket there. So we can look at that, or we can look at my rocket that is already built, kind of similar size, and we can look at the ways of doing that.
Great. I think we'll use yours to learn how to plug it in so that we don't give away the numbers for the ones that we're actually going to use as part of the challenge.
Okay. So one thing to know about model rocketry, it's been around as a hobby for a pretty long time. I think the NAR was founded in 1958, the National Association. And so over time, there have been some standard sizes of things that have been put out there. So this rocket, we'll do some measurements on it and figure out how the diameter and everything are. But I know that this is a BT-60 rocket. So the body tube is a BT-60, and that means the nose cone is made to fit the BT-60 nose cone, so all the dimensions are kind of there. So that's where using the database of parts is a little bit easier. So we'll start building this rocket. The way Open Rocket works is you build from the top of the rocket down at the nose cone, down to the bottom of the rocket, where the motor goes inside of the rocket. And so that's kind of how we'll build this one. So the first thing we need to do is find a nose cone. If I wasn't going to use a database of parts, you would select the nose cone, give it a shape, give it a size, and things like that. So there are certain dimensions on the nose cone you need to know, the diameter of the base of the nose cone, and then how long the nose cone is from the separation point to the tip. And then the bottom of the nose cone is a shoulder, and that makes it so it fits inside of the body tube. So you need to know a couple of those dimensions. So to do that, you take your ruler and measure out those dimensions. Are we metricized in this course?
Oh, that is an excellent question. Thinking that I am more familiar with standard, let's go ahead and do inches.
Try and do inches. Okay. So that's kind of interesting because this body tube diameter is 1.63 inches. So I know that from having the knowledge of that. But if you have a kit, the kit will actually tell you what the diameter of the main body tube is when you look at the package. So you'll be able to see that and say, oh yeah, well, I know that that's 1.63 inches. So you can do that. And so you can measure that out and take your ruler and put it up against the side and measure. This is about 2.5 inches long, this nose cone. So in OpenRocket, I have the nose cone dialog open. I just did that by clicking the nose cone button. And we know that the base diameter for this is 1.63. And the length of this nose cone I just measured at 2.5 inches. Doesn't quite look like the shape though. My nose cone is kind of rounded. This nose cone on the screen is a little bit pointed. So we have a couple of different shapes. A conical nose cone is just a cone with, like if you had a snow cone or something like that in the little pointy cup. An ogive cone has a shape where the sides of the nose cone come to a point and then have a nice smooth radius down to the maximum diameter. An ellipsoid nose cone is the shape of an ellipse. So there's no point. It's kind of rounded and it has a nice curve that goes all the way down to the widest point. That looks a lot like the nose cone that I've got on my rocket. So that's the shape that I'm going to choose. I talked about the shoulder of the nose cone. So that's the piece that is a cylinder that allows the nose cone to fit into the body tube. And so we'll go to shoulder, which is a tab here. And you can tell it the diameter. So this would be a diameter that fits inside of your body tube. And I am thinking that this is going to be 1.55. I think. Let's see how that looks. And I'll look at the length of that cylinder section is about 0.75 of an inch, 3/4 of an inch. So 0.75.
Quick question.
Yes.
If we hadn't been doing rocketry since we were 13 years old, how would we know it's a 1.55? Would we measure our diameter with our caliper or?
Yeah, so you can use your caliper and you can measure the outside of your rocket by using the big jaws and going on the outside of the rocket. And that will give you your outside dimension. The caliper also has small arms on it on the other side, and those are going to go inside the tube, and then you can spread out the calipers and get the reading for the diameter of the inside. Another thing you could do is, since we know that this is a BT-60 rocket, instead of building all of this and putting all the numbers in, we can go to the database of parts. And I know that this is an Estes, so I'm just typing Estes to get to my Estes things. And I know this is a plastic nose cone that is 1.63 inches in diameter and 2.5 inches long. So if I select that one, it'll actually fill all of this information in automatically. So it gives me the, let's see how far off I was, 1.595. So I wasn't too far off from my dimensions there. Now it'll tell you some information here. PNC stands for plastic nose cone, and the -60 stands for, it's for a 60 sized airframe. Those numbers are not measurements. Estes, back when they first started making model rockets in the 60s, came up with a certain designated size for their tubes, and that kind of caught on around the thing, or around the hobby. So it's just two ways of doing the same thing. You can fill it all out. You just have to measure more. You have to figure out, understand the length there. And you'll notice that this shape doesn't include this little bit of taper at the bottom of the nose cone, and that's just because when they measured the parts and put them into the database, they didn't include that. This is not enough to throw off your calculations not to have that, but in general, you want to be as exact as possible when you're modeling your rocket in the simulation, because the simulations are really cool, but they're only as good as the data that goes into it. So I'm going to use this nose cone model that I got from the database just because it's a little bit easier. But you can definitely go in and measure everything and do that. But it's helpful once you know something like the diameter of your tube, you can go out and find the parts that fit that tube. So I'll close this dialog. So that's our nose cone. That's at the top of our rocket. The next part of the rocket is the body tube. It's the airframe of the rocket. It's what holds the motor mount, the fins attached to the body tube, and inside of the body tube are the parachute and the shock cord and things like that. So what we need to do is figure out how long this piece of tube is so that we can put it into the database. A nice thing about RockSim is once you have a part like a nose cone selected, if I say I want to add a body tube, it's going to add a tube that matches the dimensions of that nose cone. So it already has the outside of this dimension, the outer diameter, from what we had from the nose cone. And it already has an inner diameter based on what we had for the shoulder that we brought in. So we didn't have to measure any of that. We didn't have to choose anything. But what it did is it gave us a body tube that's 7.8 inches long. Well, I know that this body tube is a little bit longer than that. So I have a tape measure just because my ruler is a little short. So I'm just going to measure with my tape measure using inches from where the nose cone sits on the rocket all the way down the side of the rocket. And if I keep it on the side that has inches, this rocket, this body tube is, I don't know if you can see that. Looks like it's getting fuzzy. 15 inches and 3/8. So 15 and 3/8 of an inch. Now, I'm not really good with keeping my fraction to decimal conversions in my head. So I'll use a calculator for this. So if we have 3 divided by 8, that's 3.75. So I know I have 15.375. So I go here to the body tube length and I enter that. 375. And when I tab off of that, it'll make my rocket the right size in RockSim. And what you can do is verify, because as you add things in, it changes the length. So we knew our nose cone was 2.5 inches long, and we added this 15.375 inches long period, and it gives us our length of 17.875. So we know that we're in the ballpark there. We're doing the right thing there for the rocket. So that's the body tube. And again, we didn't have to choose anything from the database. We didn't have to pick any sort of material or anything. It just pretty much knew that we were going to do a paper tube, and it gave us the sizes there. So really, so what you might run into is your green eggs and ham rocket has a plastic tube for holding the egg. That you'd have to kind of enter in that inside diameter and the outside diameter and the length. So those are places where you'd have to measure a little bit.
And that is separate from the body tube that you just entered. It would go between the nose cone and this tube.
So you would just it would just be a body tube. My rocket doesn't have that payload bay, so I just was doing it's a simpler rocket. But you would do the same thing. So you'd have your nose cone, and then you'd have your payload bay tube, and then you'd have your coupler that holds the pieces together, the transition there. And again, you'd measure those out. Let's do this. Let me make this a lot shorter. Oops, I don't want that. Let's delete this body tube. I'm just selecting it and using the delete key on the keyboard. And here I'm going to double click it and get the tube out. I'm going to make this a much shorter tube. So would you measure for me your how long that tube is?
Tube is 4.57.
4.5.
Oh, well, let me change that. It is, wow, that's not right. Hold on. 4.87.
4.87.
Yeah, I did it from top to
bottom. Great. Using that digital caliper to get you your digital number. I like that. All right. So that will have our payload bay tube in there. And so the next thing that's on that rocket is a transition. It goes from this egg tube that can hold an egg down to the body tube for the rocket. So again, we just start. Again, we're building from top to bottom. So the next thing would be our transition. So I'll click transition, and it'll start by giving me just a random transition. Roxim says, hey, you want to do a transition? Here's a transition. So we just need to change our diameters. So I'm going to kind of make it match what you're seeing, but I'm going to use a little different body tube in here, and I'm going to use a tube that is 1.3 inches in diameter. So 1.3. That's the aft diameter. Remember, our front diameter is our diameter. So we have it goes down from wider to narrower. And then how long is that transition? So we're looking at from where it sticks out from the payload tube to where it would go into the body tube.
1.28.
1.28. All right. So that's the length of the transition. So now we have something that kind of looks like the transition that we've got. And then what we need to do is give it some shoulders, because there's pieces that go up into the body tube, into the payload tube, and down into the body tube. So when we go to the shoulder, again, we can probably going to say that it's going to be close to 0.75 inches, just because of the length. And then for the diameter, you'd have to measure that diameter of it. And you can see I'm kind of just moving the slider along, and it's getting bigger and bigger and bigger and bigger. And I don't want to go too far. There we go. Actually, let's use the same diameter that we had for this shoulder. And I think that was 1.59. And so that will make it so that will match that. That's easier. That's another thing about Roxim, is once you've measured one thing, if you're doing something that's the similar thing, you can just use those measurements as you go along. And then for the bottom of the transition, we have the same sort of thing. We need to give it a value for the length of it and the diameter of it. And again, I'm kind of making some numbers up here. But you would measure that and put in your diameters as you need. So I was talking about a 1.3 inch diameter. So we'll make that 1.29. And so that would be our transition piece. And then you have to tell Roxanne, because we didn't pick it from a known part, we have to tell it what is it made out of. And I think your transition there is made out of plastic, right?
Yes.
So there's polystyrene plastic. That is typically what most of the rocketry parts are made out of.
And our payload section is plastic too.
Payload section would be plastic too. Okay. So we'd have that in there. And yeah, that looks good. So that would be our transition piece. And then to add a body tube that goes on the bottom of that, then we would go ahead and click on body. You know, if you have your transition selected, we click on body tube, it's going to add a tube to the bottom. And so I'm going to use the measurements that I took from the previous one, which was 15.375. And this is cardboard. So when I move off that, I'll now have a big long rocket. And now it would be the time to put fins on. So fins belong to body tubes. Basically everything has an owner. So you can choose a couple of different fin options. Trapezoidal fins are fins that have 4 sides and have straight angles. Elliptical fins are fins that have a curve to them. And then the freeform fin allows you to put any number of points where you decide what your fin wants to look like. So luckily, I think both of our rockets have very similar fin shapes. Yeah, close. You got a couple extra points on there to make it look snazzy. So this is what's called a clip delta, and you've got an even different clip delta shape, because if we extended these lines out, it would make a delta triangle, and we clipped off the point. So that's why it's called a clip delta. So this is an example of a trapezoidal fin. So I could use. Yeah.
Is there any inherent benefit from one shape over the other?
Not really. It tends to be, unless you're doing like super high performance, or you're going to be using a really, really powerful motor to try and make it go as fast as possible. The shape of the fin, as far as the performance, doesn't matter all that much. What the shape can control is the stability of your rocket. So there are some things like a fin that sticks out straight. So this is a nice clipped kind of swept fin. This gives you more stability than if you had the same fin, but sticking straight out from the rocket body. So there's some things there. And the nice thing about using a simulation program is it does a lot of that stability calculations for you. Back before computers were things that everyone had, there was a set of formulas, and they were created by a gentleman named Jim Barrowman, and he figured out what the stability formulas would be for model rockets based on work that he was doing at NASA for sounding rockets. So basically you take the shape of the nose cone, and there's a formula for that, and the shape of the body tube, and there's a formula for that, and the shape of the fins, there's a formula for that, and it looks at the entire shape of the rocket and comes up with what the stability of this rocket shape would be. Open Rocket is doing that for us as we go in and start looking at things. So I'm going to do a very simple fin. Again, I'm going to measure some things about the fin, and we'll talk about the different parts of the fin as we go through it. So this is a fin. We're going to make it out of balsa wood. This is a balsa wood fin. So that'll put it out there. And you'll notice what happened when I put the fins on. We got a little red dot popped up on our screen. That little red dot is the center of pressure. And so that's that's where you take all of those aerodynamic shapes and figure out those formulas and come up with, this is where on this shape, we have all of the aerodynamic pressure is equal at that point. So that's kind of ties into stability, because we have this little blue dot up here, which is the center of gravity. And that's where everything balances. So if we tied a string to this shape, it would balance at a certain spot. And what we want to have happen is we want that balance spot, center of gravity, to be in front of the center of pressure. So that's what we're seeing here with these spots. And as I make changes to the fins, you'll see that that spot will move around, because the shape of the body and the fins is what makes the center of pressure. So the fins have certain parts to them. There's the root edge. The root edge is the part of the fin that touches the rocket. So if we wanted to get what the length of this root edge is, we would just measure along everywhere where it touches the rocket. I'm just having my ruler up against the fin. And this tells me that root edge is 3 inches and 3/4, so 3.75. So here where it says root chord, I'll put in 3.75. The tip, so it changed our shape of our fins quite a bit there. The tip is the part of the fin that touches the air. So this is the end of the fin, the tip of the fin. And so I'll measure that. And that is 1.5 on my rocket. So we'll take the tip. 1.5. They're using the word chord here. Chord is just the width of the fin. So the span of the fin is how far it sticks out, and the chord is the width. And this is a taper to it. So the chord at the root is much larger than the chord at the tip. And then the other thing we have is our sweep. So my fins don't stick straight up. They actually sweep back a little bit. And so the way that you can measure this is if you get your ruler and go along the root edge. I don't know a really good way to show that. And then from where the tip is, if we go down a straight line from where the tip is, it'll intersect and tell us what our sweep length is. And this one is the same as the root chord, so 3.75. So if I put in the sweep length here of 3.75, and now we have a shape that kind of looks like that. I didn't quite get that right. It doesn't quite look the same. Oh, I haven't changed my height. I haven't changed my span. That's why it looks so weird. It only thinks my fin is 1 inch above. And so again, to measure that, you would measure from the body tube out to that highest point. And that in this model is 2.25 inches, or 2.25. 2.25. There we go. So that looks a lot like my fin. And you just draw those shapes and put those values in, and you would get that. This also only has 3 fins by default. My rocket has 4 fins. So I'll need to change the number of fins. Open Rocket makes it very easy, because you just come in and say, well, I want 1 more fin. And it adds it to that. And as you can see, my center of pressure kept going further and further back as I made the fins bigger and put that sweep in there. And that's kind of what we want. We want that center of pressure to be further back. So that's a good, stable rocket. A little bit overstable, but we still have some parts to do.
I was trying to think from my exam, it's supposed to be 1.5 the diameter for the sweep.
That's a good rule of thumb. So to make a good stable rocket, the minimum distance that you want between these 2 points is about 1.5 times the diameter of the rocket. So that's a good way to measure that. That's called a ratio of stability. And they call it calibers, but it's really just the body tube diameters. So right now my rocket is very stable. It has five body tubes between there. But we're going to have a motor in the back that will bring the weight towards the back. We're going to have a parachute in there that'll change the weight a little bit. But that's the next piece of that. For motors, motor mounts, those are tubes that are inside of the rocket that hold the motor. It's a motor mount. The rocket motor goes in there. We tape it in or use the little adapter, a retainer or a little hook sometimes to hold the motor in. And there's centering rings in there that hold the motor tube in the middle of the body tube. And so those are, again, fairly standard size items. Once you've been building a few rockets, you'll get to know them, but we have to know what our diameter of our motor tube is. Thankfully, you can look at your kit parts and it'll tell you, hey, you have a motor tube that fits an 18 millimeter motor or a 24 millimeter motor. So you get to know what those are. And there's only basically for model rockets 4 motor tubes you have to worry about. The smallest is called a BT5, and that's for very small motors. The medium-sized one is called a BT20, and that's for motors like B64s or C65s, those type of motors. The next size up is a BT50, and that's for motors like D12s, E12s, and some of the other more bigger size motors. And then the fourth most common one is the biggest one for model rockets, and that's a 29 millimeter motor. So that would be things like F motors, G motors, and things like that. So for your green eggs and ham, what's the recommended motor for that? Do you remember?
We're going to use the C11-3.
C11-3, okay. So I happen to know that that's a 24 millimeter motor. So that would be a BT50 for our motor mount. To put a motor mount in a tube, you have to select an inside tube. So it's an inner component. And we're going to use an inner tube. And again, we could measure that out and figure it out, or we can use the database. Since we know that it's a BT50, and again, I'm going to look at Estes. And so they have the description in here. It talks about all the different motor or body tube sizes. So there's a BT50 body tube right there, and we'll select that. It tells us that the outer dimension of that is almost an inch, 0.976 of an inch. And the inner diameter is 0.95. So those are things that we could know. And the tube that I've selected is 18 inches long. So if I say okay here, it's going to put this big giant tube inside of my tube. So what we'll need to do is just reduce that length. And again, you can measure the length of your motor mount before you create the rocket and know what that is. Or if you know that you want to have a certain amount of tube in there for reducing the internal volume, you can do that. I think that for most motor mounts, an appropriate length is going to be somewhere in the range of 3 inches. Some of the longer motors are a little bit longer than that. They're more like 4 inches. But for the C11s, those are fairly standard size motors. So I think we can get away with a 3-inch motor or a 3-inch long tube. But you can measure that before you put the parts together. It's a little bit hard to measure once you have everything together because you can't get to the top because it's all inside. We'll go ahead and say 3 inches. So what that will do is make it back down to a reasonable size. Now what we've got now is, and again, we can make this, it chose paper as the material, so that's fine. So that would be our motor mount. And then right now we have this tube kind of floating in air inside of the tube. So we need to connect the motor tube to the tube. And the way you do that is there's a centering ring. There's a ring made out of paper or cardboard inside of here. And so we'll need to put a ring on there. Rings, if I remember correctly, belong to the, choose a centering ring, yeah. They belong to the outside part. So remember, all of the stuff is kind of hierarchical. We go from bottom to top and we go from outside to inside. So the centering rings belong to the body tube. And when you select that, a nice thing is you can move the, I'm moving it out of the bottom of the rocket so we can see this actually happen. So right now it tells me that my outer diameter is the same as the inside of my body tube. The inner diameter right now is 0. So it's a disc. There's no holes in it. If I take the part and I move it inside of the rocket, we now automatically have a inner hole. It knows how big that motor tube is. So it makes the hole in the rocket or the hole in the ring match that tube. And you never kind of want it right at the bottom of the rocket. You typically want to have it pushed up a little bit, and you can measure that. I'm going to go with 1/2 inch. So I'm going to make this negative, and it's negative because it's measuring from the bottom of the tube up. So I'm going to do it 1/2 inch, and that'll put that ring in there. Now the problem with doing a ring, only one ring, is you don't know if that's going to be straight when you put it into the rocket because they're only holding it onto the one part. So what we want to do is put a second ring on to make it so that it's even. Have something that makes a good demonstration of that. You know, if we had, pretend this was a ring that was on there, there's nothing that stops the front of the rocket from, or the front of the tube from moving up and down. If you had 2 rings on there that were the same diameter, like this, then that tube, because it's glued on, can't be in the main tube crooked. It's a way to keep everything nice and straight and centered. That's why they're called centering rings. So we need 2 of those. So we've got 1. So what I can do is, again, go to the body tube and click on centering ring and then move that ring forward. And again, we'll want it to be about 1/2 inch from the end of the rocket, or the end of the tube of the motor mount, so that I put negative 2.5 inches. We have a 3-inch tube. So again, these are things that can all be measured, or they're in the instructions. It'll say, you know, glue a ring, you know, 3/8 of an inch from the end of this tube, or 1/2 inch from the end of that tube, and you can use the instructions to help you out with that. So those would be those parts. And let's put a motor in here. I forgot to tell this, the program, that this is a motor mount. So we'll put that in there. And one of the things you can tell it is how far the motor extends out the back of the rocket. Most model rockets will be somewhere between 1/4 of an inch and 1/2 inch. I don't know, does that one have the motor hook or does it have the screw-on retainer? It has a motor hook. So that's probably going to be about 1/2 inch sticking out of the back of the rocket. And again, you could measure that if you took your calipers and went from the end of the motor tube to where the flat part of the hook is. That would tell you the length. Yeah, the length. It's hard to do when you're trying to hold it up to the camera. But yeah, so you'd measure that way and it would tell you how far that is. But it's probably going to be about 1/2 inch.
Okay. Yeah, it's really hard to get it because it's already in there.
It's hard when it's built. I know.
Okay. But yeah, it's not long.
Okay, so we'll do that. And then, so we have a motor. That's all we need to know for that. And then what we can do is, let's take a quick sidebar into motors. I need to rename my rocket. So one thing you can do is you can name all of these parts. So my motor mount right now is called inner tube. So when you're building your part, you can actually change the name of the component. So I'm going to call this motor tube. And that makes it easier. Inner motor, okay. Motor tube. And that way we know when we go to assign the motor, we say, hey, we want the engine, the motor goes in the motor tube. So I'm going to do a new configuration. I'm going to pick a motor, select a motor. And you told me we were using the C11, right?
Yes.
So what you can do is, I want a C motor. I want it to be a 24 millimeter because I happen to know that. And right at the top of the list is the Estes C11. So we can pick that, and you can choose a delay because the C11s came in a couple of different flavors. I think you mentioned a C11-3. That's a great motor, very nice motor. And if we load that in, we now have a motor in our rocket. It's in our tube. You'll notice the center of gravity came down a little bit more. So our stability is now at 3. So again, perfectly stable rocket, perfectly fine.
What numbers are your good zone? What's the outer, like, crazy?
So the main thing is, as long as you're above that 1.5, you're going to have a stable rocket. If you get into some really crazy large numbers, 7, 8, we get into talking about stability and why you don't want a rocket to be more stable than it needs to be. Basically, if it goes into the wind, if it's overstable, has a really large stability number, when the wind hits the fins, it'll start to arc over and it won't come back straight as easily. If it's unstable, if the stability margin is too small, if it goes up, it's just going to go whatever random direction it wants to go. The kind of perfect path for a model rocket is to kind of do little S's through the air as it goes, as the wind hits it and it maybe tilts a little bit, it hits the air hits the fins, and that corrects back up until it's going maybe a little bit off the other way, and then the fins correct it. So those fins are what is making the rocket go straight. And if you really slowed it down and magnified it, instead of going straight up in the air, it would make a little path that goes like this through the air, and that's stability. But the main thing is you don't want to be unstable. So if we had a lot of weight at the back of the rocket or the fins were too small, that would be unstable. So, 1.5 is stable, 3 is pretty good, 4 is pretty good. Anything above that, it starts to be not as responsive to going back straight. So you're asking me all these other questions.
Well, now I'm thinking, this is like, okay, video number 2 is going to be wind cocking, because that's one of those concepts that just really escapes me, that it's counterintuitive.
Right.
the wind is blowing, then, so, yeah.
Yep. All right, let's go back to the body tube and let's add our parachute, because we need to have a safe recovery of our rocket. Clicking on parachute, your rocket will come with a parachute if you bought it from a kit. You would just enter in the information about the rocket. So it looks at the diameter of the parachute is basically what it cares about. The other thing is there are plenty of parachutes in the database, especially if you have an Estes rocket. They come with plastic parachutes for the most part. So I think the Green Eggs and Ham uses a plastic parachute. Yeah. And let's see, that's a blue one. So I'm going to guess that's 24 inches. No, 18 inches.
And is it gonna tell me? Hold on. There's some numbers on it.
It might.
I think it's when it was made.
So typically the directions will say, hey, you get a parachute and it's a whatever. So if you needed to measure that and figure out what the diameter is, you could either lay it out flat or you could fold it into that point and just measure the distance from the point to the edge. And then that's a radius. And you multiply that by 2 and you get a diameter. I'm guessing that's about, I think that's a 24-inch parachute. Because that looks about a foot in radius there from you holding it up. So, oh, you're on mute, Robin.
No, I was trying to say I was doing like a caliper that doesn't open all the way up. So I'm like trying to measure it 3 times down.
It looks like it. I'm going to say that that's probably a 24-inch parachute. So again, it's a plastic parachute. It's 24 inches. It's from Estes. It has some standard stuff in there. Now, the only thing we have to make sure is right now it's pushed right up into the top of our tube. And we know we have a shoulder from our transition that goes in there. So we just have to go to the position relative to the top of the tube and just let's put it down so it's not in the front. So that's our parachute. That's in there. And then let's say we're going to add an egg to this rocket, right? So we can go to our payload tube and we can add a mass object. So click on mass object. And this is, you can put anything you want in here. As far as what the mass object is, we know that we're putting an egg, so we'll call it an egg. I don't know if they put egg in here. We just have payload, so we'll select payload. And then you get to tell it how much it weighs. So the default units for measurement in here are metric, so it's going to ask you for grams. So you'd get a scale, weigh the egg, put it out there. My guess is that a large hen's egg, and I haven't been doing TARC teams for 15 years and had to measure eggs forever. It's going to be somewhere between 60 and 63 grams is a typical average egg weight. So I'll put in let's do 61 in there and kind of split that difference. And then you could tell it how long it is, how big the egg is. Eggs are usually about 2 inches long and they're about an inch wide. Actually, let's do 1.5 inches and see what that looks like. Ooh, just fits in our, so remember, just fits in our tube. And again, you just want to give it there some position. So we put a lot of weight at the top of this rocket. And so that made our stability calculation change a little bit. The center of gravity went forward. So it put it kind of in that overstable area. It's not terrible. I wouldn't fix it. I wouldn't change anything about it. It's just to be aware that if you launch it on a windy day, it will probably head upwind and stay going upwind.
Yeah, I don't know if I may have been on mute when I mentioned it before, that video number 2 is going to be wind cocking, because that's a concept that just really eludes me right now because it's so counterintuitive. So yeah, windy.
All right. So this is our rocket. We built a rocket. And again, it kept track of things. So we have our mass that it kept track of all the parts. And again, you know, there's going to be glue that is in there. There's going to be paint in there. So keep in mind that this is approximate. So you can go in and override the mass of the rocket. And after you build it, you weigh it and you tell it what it is. But we definitely have a rocket that we can fly. And you can do neat things, like if you want to look at the 3D rocket with a little X-ray view, so you can kind of look at it, see what it looks like. So we have our egg, our nose cone, our transition, our parachute, and our motor mount is in there. You can do 3D finished, and that's kind of an unpainted rocket. So you get an idea of this, do things look kind of like what your rocket looks like. And then you can go fly your rocket. And flying your rocket is, you say, I have my motor, my configuration, and I want to, sorry, I have my controls in the way. I want to run the simulation. Oops. And so it's flown our rocket, and it's given us altitude in meters, tells us our maximum velocity. So again, these are simulated values. So it's going to be close. Sometimes what you see is the simulated value would be a little bit optimistic because it's a perfect world with perfect weather and perfect air and perfect everything. So you just have to take that with a little grain of salt. But what you can do is turn that into a graph, and it will give you your information about, you know, this is the red is altitude. So your altitude that's rocket going, vertical acceleration. So how much G forces the rocket is doing, and it's vertical velocity, meters per second. So going really quickly, and then you have acceleration. Yeah, acceleration is blue. So that's meters per second squared in this graph. And we got up to 100 meters per second squared. That's going pretty fast. And then the actual speed of the rocket, again in meters per second, was pretty fast. And again, you can change those. If you wanted to see it in miles per hour, you can do that. If you wanted to see it in feet per second, you want to drop 2 feet, you can change that in the settings. But that's an idea of kind of what it takes to build a rocket, what you can do with the information.
Fantastic. We thank you for walking this through the process and explaining how to put the numbers in, because we do have the kit and we're starting with, you know, the materials and just got to get it in there. So
yeah, and the best thing to do is before you actually start building, you know, measure out the parts, and you can put them right into the software and be able to see exactly what your rocket looks like as you build it. And again, you could do things like, oh, I want to see what happens if I take a fin off, if I only build it with 3 fins, or I want to see what happens if I use, instead of a C11, what happens if I use a D12, which is twice the power. Well, the hypothesis is if I'm using twice the power, maybe it'll go twice as high. And you can do those simulations without having to go out and buy the motors and, you know, build the rocket and maybe lose the rocket in a tree or have it drift off onto a building somewhere. So you can do that all within the simulation software.